Hello and welcome, SQLBits fans and data geeks. I'm Piotr from Adatis, where I'm working as a data analytics consultant. Today, I'm going to show you a cool, still fresh but not so new feature available in Databricks called Delta Lake. And I'm going to show you not only it can simplify your current ETL pipeline, but also how it can enhance its performance by using some optimization techniques available in Delta Lake as well as in Databricks. Let's go and dive in. But before we go into the details and see Databricks Delta Lake in practice, I want to explain why is it a hot topic now in Apache Spark world, why many well-known global companies like eBay, for example, are transitioning to the Delta Lake. So historically, data engineering pipelines based their architecture on the data warehouses. Mostly, they were relational database management systems like SQL Server. And that means that we could load many different sources, structured, unstructured, even high concurrent events, directly to the data warehouse. And it was a data warehouse where the data was transformed and merged with the historical data, and later on served to analysts for visualizations for reporting purposes. And that was somehow a very good solution, mainly due to the fact that the data warehouse was a unified database management system. Besides cool things like row-level-based security, we could decide who can access the data, who cannot access the data. Um, there were ACID properties guaranteed: atomicity, consistency, isolation, and durability. In short, it means that people at the same time can read and write to the data, and they can be assured that everyone at the same time reads the same state of information. Until everything is correctly written to the data warehouse, there's no risk of reading partially written data, no risk of corrupting the corrupting the table. Sorry. Uh, what's more, data warehouse maintains metadata and data relationships, um, information about the partitioning and partitioning itself, data statistics, and thanks to all of that, we can optimize our queries to run faster. On the other hand, however, data warehouse is very expensive. So because of these cool features and properties that we have. Additionally, if we don't keep data warehouse in the cloud, we have to think about the spacing. We might easily run out of the memory and we'll have to go to the shop to buy some new disk. So we have to think about the archiving of the data. Nowadays, the core point of modern data warehouses has shifted towards data lakes when it comes to both storing and transforming the data. They are relatively cheap, scalable. They can store all data types. We don't have to think about the sizing. We can archive the data as well, but just to reduce the cost of storing it. This is not that's less of an immediate thing to do, just a general maintenance. And having data lake in our solution increase the capabilities of what we can do with the data. Unlike relational data warehouses, we don't have to specify the schema on write. We can do it afterwards. So we can load thousands of files immediately to the data lake. Later on, define the schema and do some data science job, run some machine learning. But using data lakes comes with some baggage as well. They are cheap, scalable, convenient, but there are no, for example, transactional or metadata support, no ACID properties granted. So we can run into the consistency problems. So, for example, concurrent reading and writing into the data lake, there is no guarantee of consistency. People can read partially written data. What's more, if the writing process fails, it might corrupt our data, and we'll have to spend some time on cleaning it. Um, There's no schema enforcement. So if the incoming table is of different schema, different data types there, we can easily just mess our existing data and make it unusable. There are no indexing, no optimization features as well. There's no engine that covers data statistics, keep them in one place, like we have in SQL Server. We can't create any clustered index, nothing like this. In other words, it's very hard to build reliable pipeline to Data Lake, sorry, as we can do in relational database management systems like SQL Server. So for this reason and more, Databricks created a new functionality called Delta Lake. Here we go. And as an open source innovation, it serves as unified data management system now. So it brings us ACID transaction now, and it tries to minimize this gap between data lake and data warehouses. It's fully compatible with Apache Spark, so API. So there is also we need to only make a small change to have a fully working solution with Delta Lake. And with Delta Lake, we have such cool features like indexing now, keeping and maintaining data statistics, version controlling, scalable metadata handling. Thanks to this snapshot isolation of the data, it tackles the issues of concurrent read and write. And if we run it with Databricks runtime engine, we have additional optimization mechanism, and they significantly enhance our query performance. We'll see it in a minute. But first, what is the main concept behind the Delta Lake solution? So it is based on three legs: versioning of Parquet files, gathering indexes and statistics, and keeping all the information about indexes and about the commits done to our files. They are all kept in one transaction log. So when we make any change to our existing table, like inserting new records, deleting, updating, merging, there's a new version of Parquet file written out to Data Lake. And information about this new file and about the update, who committed, what committed, when committed, and the basic statistics, they are gathered and put into the transaction log. So afterwards, we'll have in the data lake our records in two versions, in two different Parquet files. But that's fine because we have the history written in the transaction log. And thanks to that, we can go to the transaction log and ask it, please show me the data from the particular point in time. And it should give us how the data look like for example, 3 weeks ago. And what is cool about transaction log is that it is just a JSON file. So we can easily go and open it and see all the changes. So once again, key features of Delta Lake, it brings now ACID transactions thanks to the transaction log. And thanks to the transaction log also, when we cover metadata, it can be handled like data if we leverage with this Spark's distributed processing power. Now it can be handled like data because all the metadata is placed in one place and all the statistics like min, max, etc. Because of the history kept in transaction log, we can do things like time traveling, ask the engine, please show me how the data looked like in particular point of time. It provides also schema enforcement and schema evolution. So schema enforcement is like when we want to write a new table to append a new table to our existing data, but it's of different schema. For example, it has additional column, or some columns are of different data types. For example, we have a string column and the original one is integer. It will raise an error. We won't allow the appending of this different schema to our original one. That doesn't happen without Delta Lake. So that's a cool feature. And schema evolution, on the other hand, if we want this additional actually column to append to our one, there is an option and we can enable it. Merge schema, it's called. This is cool for data engineers and scientists. They can now add a new column, for example, new month sales figures to the table that they are working on, and they want to have this table to be run with the current machine learning model. But the machine learning model doesn't, it waits for the different schema. But with the merge schema option, that's fine. It will allow it and it will run without any problems. So that's cool. And we have also EP data indexing now. So Delta creates and maintains indexes and it covers the statistics, as I already told you, min, max, basic one only. And thanks to that, the engine can do the data skipping. It doesn't have to read all the files. It will look into the transaction log and see, oh, okay, the value of 5 should be only in these 5 files out of 10. I don't need to open the other 5. That's significantly speed ups the run of our queries. And we have also compaction and caching. So when we have thousands of files, it takes a long time actually to open all the files, to read the metadata and to scan the data. So regularly, if we have the auto compaction or if we run it manually, it's called optimize statement, we can run the compaction. So it will coalesce all the small files that we have in Data Lake and it will make a larger one file because it's much faster just to read one file than to open thousands of files of small one. And we have new statements that we haven't had before, like delete, update, merge, and we'll see its functionality just in a moment. But Delta Lake is an open source project, but it doesn't mean that we can benefit from all new cool features for free, unfortunately. So like new optimization mechanism, for example, optimize statement, Z ordering, etc. They're only available in the premium version, and the premium version needs a Databricks runtime engine. And it's, for example, available with Azure version of Databricks, or we can go and buy a premium version of Databricks on their website. But we can also decide that we want just a free version. We can download it from GitHub, and all the documentation what's available only in the free version we can find on the Delta.io website. It doesn't have the main difference between two is mainly about the optimization mechanism at the moment. Yeah, so now when we know more or less the basics of Delta Lake, let's go and see it in practice. Okay, so I have my Databricks notebook. My cluster is already connected with the data lake. And let's see how data table looks like and how we can use it. First, we are going to create a simple table called SQL bit, which will have 4 columns: date, session ID, title, and speaker. And we are going to save it in Delta format at the specific location on our data lake. No data, just the structure. Let's run it. So now it registered using this SQL statement. The engine registered the table in Hive so that we can now see in our data lake, refresh. Yeah, I created the SQL bits folder, and we have the Delta Lake structure. So here should be our files with the data, and we have the folder with the Delta Log. There's a JSON file created. We can go and see what's inside. Okay, cool. So we can see that there is information about who created the operation called create table. So we created a table with no data, just the metadata. We have few columns like date, which is of integer type, session ID, the integer type, speaker, which is a string. All information about the schema of our table. There are some fields for later use, like partition by. Yeah, cool. Let's go back to the notebook. So now when we have our table, we can put some data. So let's insert some dummy data like today's date, some session ID, which will be a random number, and some strings for title and speaker. Let's run once. We should have one record now. Maybe put another one. Okay, let's see how our table looks like. Okay, as expected, we have two records with two random session ID numbers. Let's take a look at the transaction log, see what happened. So we did two inserts. For each insert, we have a separate commit. Let's look at one of them. Here we go. Okay. So we can see now that the operation is different, is right. We had create table in the first commit. It's in append mode, and it added a new file packet to the data lake, and we know its size. We know how many records this file has, and what are the basic statistics like minimum values, maximum values. And because in each insert we inserted only one record, so each file has one only record. Yeah, so for each commit we have different transaction log and two files for two different inserts. So with every action we do, there is a new version created. Okay, let's now delete some records. Actually, we'll delete all the records where the speaker is Piotr Mucha. And let's, see how our table looks like now. Yeah, as expected, there is no data in it. Let's see the history of our changes. So we can run describe history statement, which give us all the commits that we did on our table. So the first one, create table, then two inserts, both write operation, and at the end we deleted the records. And all other information is how many files were created, how many rows were deleted. And what is very interesting here, even though we don't see data here, if we go to the data lake and we click refresh, we still see the files containing our old data. Although Delta Lake just created a new empty file, Parquet doesn't have data there, we still have our old data, and that's fine. Thanks to that we still keep the old data until we just need it, until we manually don't remove it using vacuum. We can benefit from time traveling. So, for example, we can try to see what was the version of the table with the ID number 1. So after the first insert, let's see give me the same thing, give me the everything from the table from the version of 1. Yeah, so here we go, we had it. And let's say that I want to specify timestamp, and now I have to provide the timestamp I'm interested in. Yeah, so let's see how the table looked like after the second insert. Yeah, we had, of course, 2 records, but the current state is this. So with no data at all. Cool. That's how the transactional look and transactions look like in Delta Lake at the moment. So let's say that we want now to actually clean our data lake and remove the files. We can do that using the vacuum operation, which has additional options like we are specifying how many days we want the data to keep on our lake. So we can specify delete everything but not but 7 days, for example, or delete everything, so we delete completely everything, so we specify just retain 0 hours. If we run that with the dry run option, so it will give us the plan of what it will delete. At the first, we'll have the warning that actually it's very strange that you want to delete everything. Usually you shouldn't delete anything that is less than 168 hours live. So we can actually turn off this warning by running this option retention duration check. And now if we rerun our vacuum operation with dry run, it will specify which files are going to be deleted, these 2 files. Okay, we are happy with that. Let's delete them. Yeah, cool. So when we refresh our data lake, as expected, yeah, it removed the files. So no longer we are able to run our time traveling. There is no data actually. So we should receive, yeah, error as expected. Cool. That was a very simple example. Let's now dive into big data. So we have this sample dataset available in Databricks called Airlines. It has the historic flights between 1987 and 2008. We have things like the date of the departure, what was the flight number, what was the career destination, all the statistics of the flight. And for each year, there is a file with the data, and each file is almost half gigabyte in size. So there are almost 100 millions of records that we are going to load. Enormous or maybe small, it depends. So first we are going to read as one file to infer the schema, and we'll prepare and we'll load all the data from 1990 till 2008. I have already run the queries because later on they took several minutes to run, so to save time I have already run them. So once we loaded the data to our data frame, this is just the data loaded from the CSV files, we are adding one more column that is missing, but we are going to use later. So we have columns for year, month, and date, but we don't have any column containing the full date, actually, like 2008 0103. So we're going to create that one, and we are going to simulate an efficiency in our storage. So we are going to save in our data in 300 small files. So we're going to repartition it. Okay, and we are going to write it in Delta format, in the order to do that, we are just using the write operation available in PySpark, and instead of usually we had here Parquet format, we are just putting Delta format, and everything is carried by the engine. Also, we are going to register our table in Hive so that we can later on use SQL version. Okay, it's already written. It took almost 4 minutes to write this few gigabytes in Delta format. Let's go and see how does it look like. So let's go to Delta folder. Already I have airline. Okay, so as you can see, just skip these two big files. Sorry. We have 300 files, each of almost 9 megabytes in size. So that's very inefficient. And let's see, how did our transaction look like at the beginning after the first commit. Let's open it. Okay, so this is a big file. There's 300 entries, indicating that for each file, which is almost 9 megabytes, Delta Lake inserted almost 400k different records, and the distribution of these records is very inefficient for data skipping. So you can see that the minimum values like year is from 1990 till, let's go to maximum value till 2008. So each file has the whole range of years. So that's very inefficient if we want to query by date, for example. Same for flight number, which we are interested in this example. It's from 1 till almost the very end. So let's go back to our notebook. If we try, oh yeah, there is a quick select count to see how many actually records we have. So we have more than 100 millions of rows. That's a big data. If we try to query our data set for particular flight number, what it does that it takes almost 20 seconds. That's long actually, because let's go to actually what happened in the query. The system had to read all files, 300, because of what I have just shown you. Each file has the almost whole range of flight numbers. That's very inefficient. Especially we have also 300 files. So there are new features available in Delta Lake. So we have the optimize, and optimize itself will run within any other options like set ordering. Optimize itself, what it does coalescing of small files into larger ones. So instead of the 300 files, we would end up with a small amount of files, but the bigger one. So it doesn't have to open 300 files, but only a couple of them. Additionally, to optimize, so for bin compacting, we can specify the ordering of the data in that files. So by using set order by flight number, what I'm telling is please reorder additionally the data in the files so that they are ordered by flight number. So all the similar values in the whole data set, they should be ordered together in the same place. So this is called the co-locality. And yeah, it's a very actually slow operation to run. It took almost 15 minutes. That's why I haven't done it on live, but already. And one more remark. So we can set ordering on any column we want, but on the columns that the data, that the statistics by Delta Lake are gathered. And by default, the engine gathers statistics on the first 32 columns. We can change that option, but the more columns we gather the statistics on, the slower whole Delta Lake then works. Yeah, so because it has to gather more data. So we run it, and what happened is that the first optimization, so compacting, it compacted from 300 files to 12 files. And additionally, it did the Z ordering on the flight number. Let's go to the Delta Lake and see what happened. This was our second operation down on the table, because we rearranged the data in files, so new files were created. Let's go and see what happened. So 300 files were logically deleted and 12 files were added. Still, we haven't defined any partitioning yet for this example to see how that ordering works. So each file has now almost 10 million of records, and we Z ordered on flights, so flight number. So we can see that the first six files, sorry, have the flight number from 1 till, we can assume, till almost 1000. Let's just double check. Yeah, so first six files have the flight number from 1 to 1000, and the other six from 1000 till the end, till 9000. So as we assume, we should benefit from data skipping. So now when we query by particular flight number, let's say 6000, if we now query it on live, we should benefit from the data skipping thanks to this set ordering. Let's go. Yeah, so it read only 6 files instead of the 12 files, because the metadata is kept in the transactional log. In the log, the system read that this particular flight number is just within these 6 files. You don't have to open the other 6. Yeah, so it took now only 3 seconds almost. There are ways to optimize it even further. So we have new feature available, delta caching. So delta caching improves performance by caching data to local disk of each of our worker we have, of each our nodes. So currently I have about 20 workers. So we can benefit from additional caching feature. There is also Spark caching available, which caches data to the memory instead of the disk of the worker. So actually we can use both caching methods, Spark caching and Delta caching. However, Delta caching is not turned on by default. So let's see the example. First, let's just select by year how many flights there were in each year, and let's see the query associated with this job. Okay, it had to read all 12 files, and at the moment it didn't do any caching, so it took almost 5 seconds. Let's enable delta caching. It's now enabled. Let's rerun our query and see what happens. Okay, there's nothing major. There's almost no change in the timing execution. But let's see in details what it did. So it also read 12 files, but now see that we have more details about what happened. So we can see that there was a writing to the cache, and the the cache writes, yeah, same thing, almost. There was a writing to the cache of almost 1 MB. And now if we, yeah, that's the same query, rerun the query. So we already cached this data to the disk of worker. Now, yeah, we have only 2 seconds, so almost twice faster, because as we can see in the query explanation, it did not the cache writing now, but it benefited from reading the cache. So cache hit was almost 1 MB, so the same size that we have written before. So that's the delta caching. We can also turn on the Spark caching, and then we can benefit from 2 caching methods. Yeah, so this is the example how we can now optimize runs using Delta Lakes. Let's just clean our data lake, as we have still 300 files there that we don't need so much. Just from cost perspective, I can refresh. It's still doing, yeah, still working. Let's refresh. Yeah, now I have a nice folder with my data. Okay. We have new statements that we can use in Delta Lake, like update, delete. Delete we already seen, and merge into. Merge into is very, very useful for developers. It hasn't been before in Databricks and PySpark. So let's see the example. We are going to use a subset of the data that we already have, our airlines one. We are going to create a snapshot of it from the particular date and just 4 columns that we are interested in. This will be our, let's say, target table that we will merge new data into. All right, so let's see in this example. Okay. Yeah, so the target table will have only 4 columns, and we are going to update the information for this specific carrier, so the L and CO for specific flight numbers. We are going to change the information about the cancellation of the flight. So we are preparing our data frame that will be our incoming table. So we have 3 records, one additional completely new that is not in this data set. So we have new carrier called SQL bits with flight number 1, and it's not cancelled. So we are going to create some temporal view so that we can use SQL statements, and we are going to register it in Hive. So there are 2 ways for using merge. We can use it in either PySpark version or nice for visually nice SQL one. So we are going to merge into our airline snapshot, our changed dataset, and if they match on date, flight number, and carrier, change the cancellation option. Otherwise, just insert everything. So let's go. And if we want to use the PySpark version, we have first to register the location to the Delta Lake, and then we have also very similar options like specify what is our incoming table, on which columns we want to compare tables, and what happened with there is a match and non-match, same logic. Okay, so we have done the merge using SQL. Let's see the result. Da, da, da. Okay, cool. So what happened is that we had two flights for which we canceled the flight, and there was no record already in our target table SQL bits. SQL bits is now inserted to our table. So yeah, new cool feature merge into is now available if you use Delta Lake. Let me quickly also show you schema evolution and schema enforcement. So quick example, let's see what is the current schema of our snapshot. So date is a date type, unique array is string, and the other two are integers. So we are going to create a new data frame that will have additional column called landed, whether the flight landed or not. And in that particular case, it's cancelled and it wasn't landed, still the SQL bits. So the schema is of the other columns is the same, but we have additional one column. If we try now to append our new table to our Delta Lake, we run into the error mismatch detected. If we go into the details, we can see that the Delta Lake actually recognized the mismatch because there is a mismatch on columns. And if we actually agree on that, we can allow this by using the merge schema option. So this is what I was explaining before. If we actually want this, we can now write once again, but with this option merge schema. And we should see that this new schema overrides the existing table. And we can see, yeah, the new column already there, which might be very useful for data scientists where they create the basic tables, but then they run this data set through the machine learning modules, which are prepared for the specific schema. And that's fine. They shouldn't be there should be no errors, there shouldn't be any problems if they allow the merge schema option. Yeah, so that's the example of use cases in Databricks. Let me now. Okay, so that's all I'm talking about today, actually. So to sum up, Delta is the file format that gives you a transactional layer around the top of Packet. So we now have ACID transactions, and combined with the Spark's distributed processing power, we can now benefit from significantly improved query performance. And thanks to the transactional look, we have new features like time traveling, new statements like merge, delete, update, yeah, bin compacting as well. And the whole project is constantly developed, and almost every 1-2 months, new features are made public, like dynamic pruning, for example, which is a new data skipping technique, or Bloom filter index, so a new index we have. Unfortunately, these new features require Databricks runtime engine, so they are premium version. But hope they will also, some of them also appear new features in open source version. Hope you liked the presentation. If you have any question, don't hesitate to contact me. Thank you.